All right, tonight what we're going to be talking about is the basics about the periodic table. How was it developed and how is it generally basically arranged? So in 1700, there were only 13 elements that had been known about, which is actually amazing in itself because they didn't have electricity. They didn't really do the scientific method much at this point. So for them to actually have identified 13 different elements with the basic instruments that they had was an amazing feat in itself. But what happened is by the mid 1800s, 70 elements had been discovered to exist. And why was this huge change in only 150 years? Well, the huge change became because of them using the scientific method and the scientific revolution. And what happened during this time is that scientists would gather information and they'd distribute that information so other scientists could then figure out an additional piece of that puzzle. And because of that, you went from knowing 13 to 70 different elements. And so with these new 70 elements, they realized that it was necessary that they started to organize these. And what did they organize them initially by? They organized them by their reactivity. And it makes sense when you think about why they would organize them by reactivity, is because that's what they were doing. They were doing these reactions. So that's what they would see. They would see this reaction. They would see that these two elements work together or work similar in how they reacted to various things such as water or each other. And then they would be put into a similar group. And so what these groups were called would be triads. Why are they called triads? Because they were made out of 3 elements. Okay, so they would put them all into these groups of 3. They thought these 3 groups were perfect. And so, for example, they would put bromine, chlorine, and iodine in the same triad, once again, because they reacted extremely similarly. But even with the groups of 3, you had 70 different elements already. So that means you had over 20 groups of these triads. So this still was very confusing. So then came along Dmitri Mendeleev. And Dmitri Mendeleev was a Russian chemist and a teacher, and he wanted to figure out the way it should be organized. What is an easier way that it would be organized? So what he did is he put all the elements down. He wrote down all their properties, such as that they knew about, their masses, their reactivities, all these various characteristics, and then he resorted them. And what he found out was that the best method to sort was by actually the atomic mass. And because of this, and because of the ability of his periodicity, or how the traits worked, how it worked so well, he became known as the father of the periodic table. So Dmitri Mendeleev was the guy who came up with the first periodic table. And how did he sort it? He sorted by atomic mass. You will have to know all of this stuff. So what was amazing about Dmitri Mendeleev, though, is that he left blanks for undiscovered elements. So how he arranged it, he figured out that between this element and this element, there actually were 2 elements that they had not yet discovered based off of purely the masses. And what happened is actually when these elements were discovered, he was actually very correct in how accurate his measurements were. The other thing that was amazing is that he questioned some of the elements' established masses of the time. So scientists had agreed that this was the mass, and due to the periodic table that Mendeleev had created, he figured out that those were actually incorrect masses that the scientists had discovered. And once again, he turned out to be basically correct. But his periodic table is not perfect. Okay, why? If I'm going to focus on like argon and potassium, but all of these 3 situations work, and these were the ones that he knew about at the time. If you look at argon and potassium, remember he is setting it out by masses. Argon's mass is actually more than potassium. But if you look at the reactivity and a lot of the other properties, argon should go before potassium. Okay, so once again, if you look at this, you've got argon should be before potassium due to all of its other properties except for mass, because argon has a heavier mass than potassium does. And it works for all of these 3 little ones that I've shown you. So looking at his periodic table, I just want to point out those two amazing feats that he did. The first one is these question marks right here. So those question marks represent elements that were yet discovered. So he had zinc as 65.2 and arsenic as 75, and based off of his trends that he realized with the masses, he felt that there should be two in between there, one with a mass of 68 and one with a mass of 70, and he proved to be correct. Another one that I want you to recognize is, like, let's say gold. Notice that gold has that little question mark afterwards, and this works with all those question marks. What he thought is at the time that this was where the scientists thought that gold's mass was not near 197. He felt based off of his charts and his index cards and note cards and how he laid them out that gold should have a mass of about 197. So that's why he put those question marks in. So it's once again amazing how he came up with this, that he figured out undiscovered elements and he figured out that some elements' masses were incorrectly displayed on the periodic table as it was. So what happened is though, yes, we've already talked about it, he did not have a perfect periodic table. And so what ended up happening is a guy named Henry Moseley in 1913 came up with a better arrangement. And instead of masses, he developed it based off of their atomic numbers. And remember, atomic numbers is equal to the number of protons. This is the one that we use today. So Moseley is the one who came up with the modern periodic table. Okay, and Mendeleev was the guy who came up with the first periodic table. All right, so now we have this wonderful periodic table. This was, once again, this one was the one that Moseley came up with. And what he did is they have to arrange it, and there are different parts that you're going to have to become very familiar with terminology that we use in chemistry when discussing the periodic table. First off is that periods are your horizontal rows. So periods are your rows. Vertical columns are your groups or families. So we call rows periods, and we call vertical columns groups or families. Okay? And so if you think about a group or a family, they have very similar chemical and physical properties. In actuality, I'm just going to let you know, we will care more about the terms groups and families than we will about periods. Okay, and the reason why is because these vertical columns of groups or families, they have similar properties, similar characteristics. So we like to group things so it makes it easier for us. That's the whole point of the periodic table, is to help us figure out properties easily. So we will be focusing on those vertical columns or groups or families. How can you remember that groups or families are similar in properties? Well, if you think about a group that you're part of, such as, like, let's say environmental action. So if you're a part of environmental action, you guys have a similar interest level in the environment, and that's what makes you a group. If you're part of the same family as each other, you guys have similar characteristics, similar interests, things like that. Okay, so that's where you get this, that the vertical columns, how you can remember the groups or families, have similar properties, both physically and chemically. And the reason why is because they have the same number of valence electrons. Now, we haven't really gone over valence electrons, so I'm going to be spending the next few slides talking about it. But they have the same number of valence electrons, and this is key. So when I ask you, hey, which one has the more, which one is more similar in characteristics, groups or periods, you need to say groups. And the reason why is because, and you say they have the same number of valence electrons. And this is, valence electrons are the only ones that are involved in bonding, are the electrons that are involved in bonding, and that is why they are the ones that dictate all of the physical and chemical properties. Now, I would like you guys to note, when you look at periods, you would think, as most people would, that the one next to it, or like let's say this guy, would have a more similar property than the one below it. Why? Because the atomic number of a period is only one greater, whereas when you're going down a group or a family, you're talking it's got an atomic number 10, 18, 36, more than the one that it's right above. So you would be like, oh, but their atomic numbers are very similar in periods and they're not in groups. Doesn't matter, because once again, it's not based off of their number of protons. It's based off of their valence electrons for most of these properties. All right, so what the heck is a valence electron? Well, valence electrons are the electrons of an atom that are involved in bonding. These are the only ones that are gained or lost during a chemical reaction. And that's what we care about as chemists. What can you lose or gain? Which electrons are involved in these bondings, in these chemical reactions? They are the outermost electrons. Okay, so they are found on the outermost orbital level. You can have a maximum of 18, except for the first row or first period has a max of 2. Okay, by the way, a max of 8 is known as an octet. 2 is known as a duet. So everybody is always striving to get that octet. And once again, they are the most important electrons. These are basically the only ones we really ever care about as chemists because these are the only ones that are involved in reactions. All right, so let's talk about how to calculate how to figure out the valence electrons. So I'm going to do an element, it doesn't matter which one. So here's my nucleus, and I'm sure you guys have all seen this as far as an atom goes. Okay, so we've got all these different rings of an atom. And on these rings, we have some electrons. So in the first, you can only put 2. In the second one, you can put 8. Okay, and then we're going to put 8 here. I'm not going to put 8 actually, but I can fill up to 8. So I'm going to put 3, which means that there are 4, 5, 6, 7, 8. There are a few openings still available. So if I were to ask you about this particular element, I would say, hey, how many total electrons do you have? So when you add them up, you had 2 from the initial, you had 8 from this guy, and you had 3 from the outermost. So that would give you a total of total electrons is 13. Now, if I were to ask you your valence electrons, and you look at the characteristic of what a valence electron is, they're the outermost electrons. So what's interesting about this is that I do not care when I'm asking for valence electrons about anything in this group or anything in this group, because these guys are the ones in the outermost. So how many valence electrons does it have? It has 3 valence electrons. Okay, so all you have to do is look at an image and then count however many are on the last ring. So with this one, we'll talk about, here's my nucleus, okay? So my total number of electrons, that's not how you spell total. Total is 1, 2, filled up that whole row, 3, 4, 5, 6. So it's got a total number of 6 electrons. But when I want to focus on just the outermost, which are the valence, I'm only focusing on this little group right here. So how many are there? 1, 2, 3, 4. So it would have 4 valence electrons. All right, so what's really interesting is, and cool, is that it kind of goes on your periodic table, it goes in order. So as long as you can count from left to right up to 8, you should be able to easily get fill this in. So what I want you to do is take out your blank periodic table or non-colored periodic table, and we're going to write our first things on this. And so what we're going to be doing is above each column, write down VE, and that's going to stand for valence electrons. We're going to write the number 1. Notice that everything in this entire family or group or column all have 1 valence electron. The second one would have 2. Skip 3, 4, 5, 6, 7. Now what I want you to understand is that this guy, because it is helium, it only has 2 valence electrons, but everybody else in that group or family has 8. Okay, so mostly they'll have 8, except for this guy, which is your duet, only has 2, and then every row after that has your octet, which is 8. Okay, now what I want to focus on is I want to draw what happens to get these little charges that we've talked about. Okay, and it's all based off of your valence electrons. So if we have I'm going to draw carbon again. No, I'm going to draw oxygen. Okay, so we have our nucleus, we have our 1, 2, and then oxygen, 1, 2, 3, 4. Okay, so this is oxygen basically right here. Okay, so it has a total of 8 electrons, and then it's got 6 valence electrons. What happens though is that it has these little openings right here. Okay, so what it does is every element wants to have 8 electrons, or it wants to lose all of its valence electrons. So it either wants to gain enough electrons to make 8 for its total valence electrons, or lose all of those valence electrons. So if I look at oxygen, okay, oxygen has 6 valence electrons. Okay, so it could either lose 6 valence electrons, or it could gain, well, how many would it gain to make 8? Well, looking at my spots, it would be 1, 2 that it would need to gain. So gain 2. So which one is it going to choose? Well, it's going to choose the least of the path of least resistance. So that would be to gain 2, which means its charge would be a -2. Okay, let's try another one. Let's try boron. Okay, boron has a total of 5, not valence electrons, but a total of 5 complete electrons, which means that boron has 3 valence electrons. So I'm talking about this guy, and it has 1, 2, 3, 4, 5 openings. So it can either fill in these 5 little openings, or it loses its 3. So it can either gain 5 or lose 3. Which one is it going to choose? It is going to choose to lose 3. Why? Because it is going to choose the path of least resistance. Losing 3 is easier than gaining 5. Okay, and why does it only lose or gain those valence electrons? Let's look at that. Well, when we look at the valence electrons, where are they located? They're located on the outside. Okay, they're going to be a lot easier to add to or take away than any of these guys in the inside. Okay, think of like when you're peeling back some sort of fruit. It's going to be a lot easier to peel out these outermost layers than it is going to be penetrating into the innermost and peeling those first. So what ends up happening is that they only focus on the outermost because the outermost are easily accessible. Okay, so what you can also notice is if I did this type of situation where I'm adding 3, taking away 5, whatever, okay, what I want you to note is that it follows this general trend. Anything with a 1 valence electron will choose to lose that 1, so its charge will be +1. If it had 2 valence electrons, it can either gain 6 to make 8 or lose those 2. So it's going to choose to lose 2, which means it's got a +2. Anyone in this column is going to have a +3, as I just showed with boron. This column of the carbon group is a little interesting. Because it has 4, it can either lose all those 4 to make 0, or it can gain 4 to make 8. And it kind of depends on what it's doing, who it's bonding with, what it's reacting with, what are the conditions, to whether it'll lose or gain. Okay, so it actually has both. 5 for this column, or like nitrogen, will either choose to gain 3 to make 8 or lose the 5. So it is going to choose to gain 3. -2, -1, and these guys are all 0. They never ever react. Why? Because they already have their 8. They ain't going to change. They're not going to lose any. They're definitely not going to lose 8 in order to get to 0, and they're perfectly happy with gaining nothing because they are perfectly happy at having their full octet or duet in helium's case as it is. So what I want you to do on your blank periodic table or non-colored periodic table or your cheat sheet periodic table is I want you to write these charges right above all of the families, just like I have done. All right, hopefully you have a basic understanding of the intro to the periodic table, charges, valence electrons, periods and groups, and a general understanding of the history. Have a great evening.